Welcome to this video series on electricity and magnetism. Over the course of the series, we will be, from a calculus-based perspective, exploring electromagnetism with applications to circuits. We will also be taking a look at electromagnetic waves and seeing how that gives rise to special relativity and the equation E equals mc squared and what that means. Revisiting light waves, we will then head off to explore both wave and ray optics. So to start with looking at electromagnetism, we're going to start by taking a look at electric forces and electric charges. And so we will start with the electric charge. And I would like to take a bit of an inquiry-based approach to that. So if you happen to have it available, it would be nice if you could find some transparent tape, such as Scotch tape, but honestly any brand will do, and in fact the cheap stuff works better. So some transparent tape and some paper bits. So you can just take a bit of scrap paper out of the recycling or whatever, just tear it up into some small but not confetti, bigger than confetti, but maybe centimeter on a side kind of pieces of paper. And you don't need a lot of them, just a few. So with the tape, what I would like you to do is, if this is a reasonably clean table that you happen to have around, take one piece of tape, lay it down, I'd say maybe no more than half a meter, 30 to 50 centimeters long, something like that. Then double back and tape to itself this a little handle, if you will. On the top of that, and stick it down onto the tape. You need the handle taped back onto itself so that this bit won't stick to the table, so you can pull it back off. Write a letter L on the top of the handle. Then, with another identical piece of tape, maybe just a few centimeters shorter, I'll draw it in a different color just to make it clear, tape that piece on top of the first piece, and again fold a little handle like so, taped right to it, and on that write the letter U. Now in the next steps here, once you've taped both of those down, grab onto the lower handle and detach both pieces of tape at once from the table. Then once you've done that, the very important step that you have to do, and we'll get into why it mattered in a bit, but the very important step that you have to do is run your hand down along both sides of the pair of tapes. Then once you've done that, quickly yank the two pieces apart. Go tape them off to the edge of the table or something like that and make another pair. Then what I would like you to do is, with your pairs of tapes, I'd like you to hold different kinds of tapes next to each other. So, and you can make yourself a little table here. So you can have a U tape and L, you have a U tape and L tape and paper, like so, U tape, L tape, paper, paper, like so. And what I want you to do is, in each case, just bring the appropriate objects near each other without actually touching. So if you want, you can go ahead, pause the video, take a look at what's happening, and just kind of put notes into your table. When you get done, go ahead and unpause the video and we'll review what happened. So you should have seen that two U tapes next to each other repel, and also two L tapes near each other repel. You should have seen if you bring a U or an L tape near each other, they attract. And then you should have seen that if you bring a U or an L tape next to a piece of paper, it attracts, but weakly. And same if you bring a piece of paper near a tape, it attracts, but weakly. And then if you bring two pieces of paper next to each other, nothing happens. Now, what I would like you to do for a moment is pretend that you don't remember anything about electricity from any previous science classes. I'd like you to just think about what you can conclude about the force that must be acting between these. So think about that for a bit, pause the video. Once you've had your thoughts, we'll go back and discuss. So hopefully you should have had some of these thoughts. First off is that you realize that this force isn't gravity. Whenever you think you might have discovered a new force, it's always a good idea to ask yourself, are you sure it isn't one you know before? So thinking back to your mechanics, you should ask yourself, is it gravity? And you'd say no. And why is that? Well, we know that gravity only ever attracts, and here we see cases of things repelling. So it's not gravity. So it's something else, so we'll give it a name. We'll call it the electric force. So what else can we conclude about this electric force? One thing we can conclude, or at least start to get an intuition for, is that it's a long-range force. So it's like gravity in that respect. There doesn't seem to be like any kind of separation where the force immediately cuts to zero or something like that. And in fact, that is the case. Every object in the universe is interacting with every other object in the universe electrically if they have a charge. We also can tell that the force gets stronger as you get closer. Now, some other things to think about is apparently what's dictating the strength of this force is not the mass of the tape. It's what we call the electric charge. Now, you may, if you want, you can try making another pair of tapes, but say be a little less, a lot less vigorous actually in how you pull the tapes apart. You'll probably notice they don't attract and repel as strongly. So there's some physical property, which we'll call the electric charge, that dictates the strength of the force. The more electric charge each of these objects have, the greater the force. Should also probably be recognizing that the charges got made in pairs. This is actually why we had to have you run your hand down the tape pair before you ripped them apart. because when you pulled that L tape off of the table, you actually made some charge. What happens is that the adhesive, there are long chain polymers in the adhesive, and these chains get disrupted and leave behind ionized bits of adhesive molecule. So that means that when you ripped it apart, you made the tape and the table have opposite kinds of charge. When you ran your hand down it, what winds up happening is that you were able to neutralize the pair of tapes, and we'll get a bit more into how that works in a minute. But you're able to neutralize the pair of tapes so that when you rip them apart, what happens is you have just as many U-type charge as you do L-type charge. So from this, we can also start to conclude that neutral objects are made of equal amounts of the two kinds of charges. And you can conclude that from the fact that when you rip the tape apart, you had what was a neutral object, and now one is U-type and the other is L-type. But you can also conclude that from the paper bits and the fact that they always attracted. This turns out to be because the two kinds of charges got separated a tiny little bit, and that separation was enough to cause some attraction, and we'll get more into that as we go on too. So we seem to have two types of charge, and if you think about it, the neutral couldn't have been a third kind of charge because we could never get to repel, and the neutrals didn't interact with each other. And since they're always made in pairs, this is where Ben Franklin, who was doing research in this, had a clever idea. He decided to give the charges the names positive and negative, which is really clever because if you're making equal amounts of each type of charge all the time, then you can just add up what you had before and what you had after, and it should be the same. Now, just to point out, charges don't always have to work this way. You don't always have to have two kinds. For instance, with gravity, there's only one kind of charge, the so-called gravitational mass of an object. That's the m in F equals mg. The m in F equals ma is the inertial mass. And just as a reminder, it's an experimental fact that the two of them seem to be equal to each other. And physicists assume equality, but we still keep double checking on that occasionally. And the strong nuclear force, as an example, this is what holds protons and neutrons together in the nucleus against the repulsion of all the positive charge in the nucleus. There it turns out that there are actually three kinds of charge. And they've been given the names red, green, and blue, although that has nothing to do with actual colors that you see. So it didn't have to be that there were two charges, but since there were two charges and they're always made in pairs, this idea of calling them positive and negative so that you could see the books balance before and after some process was a bit of genius. Now, which one's which is arbitrary. And you'll notice I haven't told you which kind you had for your UNL tape, and that's because I don't know what brand of tape you bought. It turns out that Scotch tape and the really cheapo stuff that you buy use different adhesives, and you wind up having different positive and it turns out that the UNL tape could be either positive or negative depending on the type of adhesive you have. So anyway, Franklin's convention, he said if you take a glass rod and you rub it with silk, that charge left on the glass rod would be positive. And it turns out that the charge left behind on the piece of silk is negative because you always make them in equal amounts. And he decided that if you took a rubber rod and rubbed it with wool, so this is what happens, say, if you take a comb and run it through your hair real fast. That the charge left behind on the rubber rod was negative, and that means that the charge left behind on the wool is positive. When we get to electric circuits, you'll probably find yourself at a point where you will really, really wish that Franklin had made the other choice. This is because it turns out that in most, but not all, electric circuits, the mobile charge carriers are actually the negative electrons. And these minus signs will create some havoc because we'll wind up having to say the conventional current goes one way, but the electron current goes the opposite way. But we can worry about that later, and I'll also point out that there are certainly systems, such as the nervous system, where the charge carriers are indeed positively charged, say positively charged potassium ions. So somebody's going to be unhappy with the choice, but this is the choice that Franklin made, and it is the choice that everyone uses to this day. Alrighty. In the next video, we will go ahead and take a look at the electrical properties of materials and talk a bit more about how we can charge them and charge polarization. Catch you in the next one.